basically because I even go out and enjoy yourself. Consider like the other thing I save money for a raise.
Let's get started. Let's get started. Let's get started. Okay. So we've been working on this situation regarding the area of a square. Okay, so I have defined up here f of x equals x squared. If x is greater than or equal to 0. So what is this function f? F is what? What function is f?
General?
What's that?
In general or
Anything. So, yeah.
Rate function?
F is the rate function. F equals x squared regarding the area of a square. That's the rate function. Agree with that? Some nods? What about in the back? F of x equals x squared. That's the rate function for an area of a square.
No, it's accumulation. We're going backwards. So it's the opposite of that.
Well, it's not if we're going backwards or forwards. It's look at the function. F of x equals x squared regarding the area of a square. Is that accumulation or is that rate? Accumulation. Okay. Okay, so it's an accumulation function. It outputs the accumulation. What accumulation does it output? What accumulation does it output? Sure. Okay, but so it outputs, so the input is x. And what is x? Side length. So it's going to output a value for a side length. How can we think of that output as an accumulation? So it's going to output, it's going to have an output for a given side length. How can that output be thought of as accumulation? Chelsea?
Because for every increase in the side length, it's going to increase the area by a little bit.
Okay, that's true. That's how we think of it as an accumulation function. But if we put an x in, say we put 4 in, we're going to number out. What number do we get? Okay, yeah, so we get 16. How can that 16 be thought of as accumulation?
Oh, that's a total up to 16, the total accumulation.
Yeah, so it's going to, the output is going to be the accumulation of area as the side length did what? From 0 to 4, right? So it outputs the accumulation of the area of a square as the side length increased from 0 to 4 was just an example, right? So as we increase from 0 to x, right? Okay, and then we, last time in class, we built this function, r of x. What is this function? So f of left of x plus delta x minus f of left of x all over delta x. Somebody knew, what's this function? David, you know what this one is? This one, r of x. Okay? He's saying it's a rate function. Agree with that? Okay, so this is a rate of change function. What does it output? Yeah, we're good. Okay, so given a side length x, he's saying it outputs the rate of change. We want to be more specific though. So that's right. It's going to output a rate of change.
But it's going to be the rates of change over certain length intervals. It's because it's going to be a step function.
Okay, so is it the exact rate of change of our accumulation function? No. So let's just look at this quickly. So remember, what did we have? Let's try that again. So for instance, we found things like that. Exact rate of change of our accumulation of area? No, approximate. So exactly in that interval, what rate of change is that? We didn't mention this before, but what rate of change is that for that interval of x? It's constant. So those of you who've had 170.
It's like the changes in y that are proportional to the changes in x.
Okay, that's true. Delta, we found it by taking the change in y, the relative size of the change in y to change in x. Okay, this is the average rate of change. So when we were finding these approximating constant rates, we were really finding average rates of change over the interval. So what is an average rate of change? It's the constant rate that would realize the same change in y for the given change in x. You see? So is the true accumulation varying at a constant rate there? The true accumulation? Or is the rate changing? The rate is changing. So all an average rate is, it's the equivalent constant rate. It's the constant rate that will give you the same change in y over the given change in x. And that's what we were doing. We just didn't name it that, okay? So it outputs the average rate of change. Rate of change of what? What quantity are we looking at the change of? All right, is it looking at the average rate of change of x values? Yeah, Daniel.
The average rate of change of area compared to the rate of change.
Okay, yeah, so it's a rate of change of the accumulation of area, right? So it's the rate of change of accumulation of area over what interval, right? So it's over a certain interval. It outputs the average rate of change of accumulation of area over what interval? Starting where and ending where? Tyler.
Left end of delta. Oh, the left end of the interval where x resides. So, the right side of the interval.
Okay. So from left x to?
Left x plus delta x.
To left x plus delta x. Okay, we can write that this way with brackets, right? So brackets indicates this interval. Okay, so we're getting ourselves oriented here. We got our original function, that's our accumulation function. Now outputs the accumulation of area of the square as the side length increases from 0 to x, right? It's the total accumulation up to that side length reaching the value of the input x, okay? And then this gives us a rate of change function. Specifically, it outputs average rate of change. It outputs an average rate of change for the interval that x is in starting at left x to left x plus delta x. Okay, what about a? So now we were looking at a as 0 before, but now I've got a on a slider. What about the value of a? What does that mean? A given x value. So is it an x value or a y value? It's an x value. So what x value is it? Yeah, DJ.
Starting x value.
Is the x value from which we begin accumulating of x. Okay, so what we want to look at, and so we've got our delta x there. Delta x we know is our interval width, right? And so it's the width over which we calculated these average rates. I think, what did you do it for last time? 0.2? You did it for delta x at 0.2. But we know that we need to change that. We need to adjust that delta x. Okay, there's our left function. Okay, so how does this rate function work? If I were to graph this rate function right now, I've got my delta x at 1. So I'll just put a like that. So I've got delta x as 1. If I were to graph this rate function, starting at 0, what would we see? Okay, so tell the person next to you. So I've got delta x set at 1, and here's how I've defined the rate function. And so if I were to turn this graph on, y equals rx, what would we see? So talk to the person next to you. What would you see?
No, that's just gonna generate. That's not gonna.
Yes.
Okay, so right now I'm showing r of 0.8. What if I put in r of 0.4? So right now it's showing that r of 0.8 is 1. So that value of 1 is, it's the average rate of change, right? It's the average rate of change of the accumulation of area over an interval. So what if I put in r of 0.4? They're saying in front it's going to be the same. Is it going to change or be the same if I change this to 0.4? What do you think? Same or change?
Same, because it's still in that 1.
What about 0.7? Still same. 0.9. Okay, what if I put 1 in there? So it jumped to what about 1.4? So what kind of function is r? It's a step function, right? Because what about these average rates of change? So r is giving us average rate of change. And what kind of rate of change is average rate of change? Constant rate of change, right? So each one of those average rates that we calculate in each interval is a constant rate of change. So if we graph those, we're going to get constant rates, step function. Okay. Okay, so now we want to talk about the effect of changing a. So what will happen if I change A? Right now I've got the slider at -10. So A is where we begin accumulating from. Okay, so if I start accumulating from a different spot, what effect will it have on the rate function?
Shift it over.
Shift it over.
All those negatives.
So it's just gonna, this whole thing is just gonna move over like this. Beth, what do you think?
It's just, it's gonna be the same, it's just, we're just not gonna see the negative one.
It'll be the same, we just won't see the negative. What is A? Point at which we start at. How does it affect the rate of change of f for these values? Say, starting at 0 up through, we're looking at about 0 through 5 here, or 0 through 6. How does changing A affect the rate of change of accumulation, say, for the values from 0 to 6? How does it affect the rate of change of the accumulation for those x values? It doesn't really, right? So what are we seeing here? So I'm changing A. So for instance, right here, you remember we start at A, and wherever we start from A at, that's where our first interval starts, right? So then you got to think of it as A and then your delta x, right? So I've got delta x set at 1 here. And wherever we put A, that's going to be the left side of the first delta x interval. So changing A, what does it change? Changes the starting point, but then, so then what does it change in the scheme of things, in the grand scheme of things? What's that?
It's gonna change where all of your intervals are.
Just where the location of the intervals, right? It's not going to change delta x. It's just going to shift the delta x intervals either right or left, right? So for instance, right now I've got A at 2.6 and delta x is 1. So there's 1. So here's one delta x interval. Yeah, whoops. Can't push the button on the pen. Messes it up. Every once in a while I forget.
We can't see the -10 side because we set x greater than or equal to 0, right?
Yeah, I'm just graphing the rate. So I'm just always starting the rate graphing at 0. Okay? But oh, I got A at 2.6, so that's fine. Back here. Sorry. Okay, there we go. All right, so here's A at -4.5. So we got A at -4.5, okay? But then we're just showing the rate graph starting at 0. So I've got this delta x here and delta x here. So what effect does changing A have? So I'm going to change A now. What happens if I change A? Think of this up here. So I just changed A. What happened? Yeah, just all your intervals just shifted. Does it change the rate? No, so the rate is the same. So our approximation of the rate will get changed. Okay? And so that might make a big difference for these large values of delta x. But I'm going to keep changing A now, watch. So what was it, -4.2 when I started?
4.5.
-4.5, thank you. Okay? So here's -4.2, -4. So what did I do? I just moved A forward 3, and what happens? So now I just shifted A forward 3 from -4.5 to -1.5. And what do we have? The same step function, okay? So what happens then if we make delta x smaller? So if I make delta x smaller, and then I change a, what effect does a have for small delta x?
It still doesn't change the rate.
Doesn't change the rate. And then for really small delta x, where we start accumulating for, in terms of the rate function, doesn't really have any effect. You see that? Okay? It doesn't matter where a is. That's right. Say, yeah, go ahead, say it longer. Say. That's right. The intervals are so small that a shift doesn't really mean much, right? It doesn't really have any meaning. Okay? Okay? So the value of a does not matter for the rate function for small values of delta x. Okay? And that's what we're showing here. So if I got a small enough value of delta x, that's the smallest one I think will show up. Changing where we start, it doesn't matter. So that being the case, then for small values of delta x, we can just replace this left x here in our rate function. We can just replace left x with, when delta x is really small, if a doesn't have any influence on the rate function, not dx, this isn't a change in x, so yeah, just x. Should make sense. So when delta x gets small, we can just change that left x just to x. And so what we're talking about now is we're talking about an exact rate function. I told you it'd be a quicker journey back, right? How about 2 days or 3 days compared to a month, right? Because we had all these tools that we understood. We understood the left function, a, everything, all those tools. So, and now we've got graphing calculator, so our journey back is a lot quicker.
So we're already jumping from an approximate rate of change to an exact rate of change function.
Not quite. What is this? It's from this to this. Exact or approximate?
As exact.
Exact accumulation. And now we're talking about for small values of delta x. Exact or approximate?
That'd be an exact rate of change.
Exact rate of change. Exact rate of change.
So that was my question. Going from left of x to x, that's going from the approximated rate of change to the exact rate of change.
No, because you still, and also delta x being small. See, look here. So just changing it to left of x. If this delta x is 1 or something not small, it's still an approximate rate of change. It's also got to be delta x small. Also got to be delta x small. Okay, and so we all saw where that was heading, right? But now, so what about this now? Yeah, we don't need this anymore because, yeah, if our delta x is so small, okay. So now we're talking about, what is this? This is the rate function for the accumulation of area. When the side length is small, what about the rate of change of area? So for small side length, say 0.5, this is telling us that the rate of change of area is 1. But when the side length is 4, what about the rate of change of area? Much greater, right? So as side length increases, this is showing us that the rate at which the area changes increases, and increases in a linear fashion. That's what it looks like anyway. That's what it looks like to us from here. Okay. So really, we've been talking about, although we haven't said it, we've been talking about the idea of limit. So some of you might have been a little nervous when your friends in other calc classes had started with limits. It's like, why aren't we starting with limits? Well, we've been talking about limits the whole time. Okay, so there's kind of two ideas of limits. So one idea is letting things get very, very small, and the other idea of limit is a sequence that never ends. Okay, so this is kind of this picture is kind of an illustration of that. So where is she truly? Where is she truly?
Left corner.
Is that truly her right there?
Well, it could be a mirror.
No.
Taking the picture.
No. She's not.
Whoa.
So where would she be?
No, she's where we are.
No, she's here.
She'd like here, right?
Yes.
She'd be like here, right? Okay. And so this is showing the idea of a never-ending sequence. Okay, as the light reflects, it can reflects forever. So if there was enough light and the mirrors were perfectly parallel, it would be never-ending, right? So there's a little bit not quite parallel, and we run out of light, right? We run out of light for that distance. Okay. But this is the idea of a never-ending sequence, and this is the idea of limit. Okay, this is the idea of limit. Okay. All right. So, agree or disagree? If the symbols A and B represent different real numbers, there's always possible to find a number between them, such as A plus B over 2, which is the number halfway between A and B. Would you agree or disagree with that statement? So if A and B are different real numbers, you could always find a number between them.
Agreed.
Like it? What if they're really, really close together? What if even closer than that? Okay. You can always find the average of two real numbers, right? And that would be a number between them. Okay? Agree or disagree? The symbols A and B each represent a real number, and it's impossible to find a number between them, then they must be the same number. So if you have if A and B each represent a real number, and you can't find a number between them, they must be the same real number. Agree or disagree with that?
Correct.
Correct. Okay.
Agreed.
All right, so this represents a number. So this is the idea of infinite sequence. 9 over 10, plus 9 over 100, plus 9 over 1,000, plus 9 over 10,000, etc., forever. Okay? So find a number between that number and the number 1. Find a number between those two numbers. Okay, can you tell me a number between those two numbers?
Add another 9.
What's that?
Add another 9.
Put another 9. So if you put another 9, it'll be between this 1 and 1. But what is this number again? Add another 9 to what?
Oh man.
Well, the dot says that it just goes on.
Keeps going on forever. So this number is 9s forever. 9s forever. 9 over 10 plus 9 over 100 plus 9 over 1,000 plus 9 over 10,000. Keep going like that and never stop. So find a number between that number and 1. She says there's not one. Josh wants to give it a try. No. 87, because the point 999998726. How many 9s do you want?
Keep going.
It's only one.
And right there.
Right there? 8726. Okay.
Still different.
Is that, so do we find a number between these two numbers?
That's less than the first number.
Oh, God.
The 9s keep going for time.
Okay, so the actual,
That's so close to 1 that the difference between would be like something minuscule, but it's still different. Well, it will be 1, but it will be
It is
extremely hard to
essentially
find
1.
because that's so close to 1.
so it's essentially 1. Okay, this is what I'm hearing. Essentially 1. So close to 1.
Yeah. That drop
What do we think?
would be 1.
So, is it 1?
No.
No. Then find me a number between this number and 1, because you agreed with me when I said if A and B each represent a real number, and it's impossible to find if you can find a number between them, then they're different. So what's the number between this one and 1?
We need to find.
The first one, like you have two completely different whole numbers. Like you have like one.
No, these are real numbers. These are real numbers. Real numbers. That can be irrational, rational, anything. On the whole number line. Rohit.
Yeah.
Do we agree with these two? Yeah, go ahead. No, go ahead. You can find an infinite amount of numbers between these two. You can. There's an infinite number of numbers between this one and this one. Okay, give me one. Give me one number between this one and one. Okay, is that between this and one?
No, that is.
It is.
I need a number between them.
Just leave off 1.9.
What's that?
Just leave off
0.9 and a
Take
half.
off a 9. Then is it between these two? No, then it's less than this.
0.9 and a half.
But if you ask one to.
Because if you have one, it could be close to one.
That's right.
Something in between.
So there's no number between, it's just a different series of 0.9.
So, is there a number between these two?
No.
No. So if there's not a number between them, are they the same number?
No.
Dan.
You messed me up.
Oh, sorry. Every day I do that, right?
No, there isn't really one.
So there's an exception to the rule. If there's a number, it's right if the numbers are completely different, but if it's so close and it's not.
Well, I mean, think of this way. If it was like 0.98, then that'd be between. If you could do something different.
DJ, did you find something that helps with this question?
Googling it right now.
There's nothing between 0.9 and
Anybody else want to weigh in? How many people think they're a different number? They're not the same value.
I have to say so.
How many people think they're the same value? What do the rest of you think?
There's a fact that they're not the same. 0.9 isn't 1.
What's that?
I'm giving up. It's the same number.
You're going for the same number.
0.9 isn't 1.
Okay, these are.
Okay,
They can't be the same.
What's that?
0.9999999 is not the same as 1, but it gets 1 is the limit of 0.99999.
But so this is exactly the idea we're saying with limit. That a limit is talking about two representations of the same number. That's what we want to think of when we think of a limit. Two ways of representing the same number. These values are equal. These values are equal. Point. An infinite number of 9s. You can't find a number greater than this and less than this. Therefore, they're the same number.
Oh. That's like saying if I give you $1 and I give you 99 pennies. You don't have a
No.
dollar.
It's not saying that at all.
99.99.
You're comparing 0.99 to 1. Are those the same number? No. Those are not the same number. You can find a number in between. But you cannot find a number in between this number and 1. Because the 9s go on forever.
Compared to this point.
Okay? They are equal. They are equal. Okay, why are they equal? It goes back to these two statements that you all agreed with. You all agreed with these statements. Okay? If you can't find a number between them, they're equal, and that's the case. All right, so here's how we use, this is what's called limit notation. So here's how we can represent that infinite number of 0.9s. 9/10 plus 9/100. And then we let n go to infinity. So we're saying this denominator here just goes to as many zeros as you want. So it's just as many 9s as you want. Okay, an infinite number of 9s. So it's two representations of the same number.
So just to get it right, you said so if you can't find one, then they're equal, right?
If you can't find a number that's in between the two,
Okay.
that's greater than this one and less than that one, then they're equal.
But
Yeah.
then does that only work with numbers that are infinite, that are never ending, obviously? Or is there
You
any
just got to
other
think, this is a value. This is a certain value when you let those 9s go on forever. Okay? And it's the same value as 1. So it's not the fact that it's infinite or not. It's just this has a value. And that if you let the 9s go on forever, that value is the same as 1.
So if it was 1.99999 forever, that would be equal to
That's equal to 2.
Okay.
Yeah. Okay, so we had the function f of x. What was our accumulation function? X squared, okay? And we came up with the fact that we said that our rate function essentially for small values of delta x, left x just can become x, and we have this. So what is f of x plus delta x? If f of x is x squared, what's f of x plus delta x? X squared plus delta x? Is that what that is? No, this says take the input and do what to it? Square it. What's the input? X plus delta x. So what are we going to do?
Find that change.
Functions tell us what to do with the input. This function tells us to do what to the input? Square it. So what is our new input? No? What's the new input here? X plus delta x. So what does this tell us to do? Yeah. Square the whole thing, right? Square the input. All right, so that's where we get this from. Okay? So take the input and square it. And then subtract the original function over delta x. So let's expand this. So we could expand this algebraically. Okay, so I just FOILed out the left. What happens? X squared minus x squared? Jeez. Stop. X squared minus x squared leaves me with this. And notice there's a delta x in all of those. So you can factor delta x out, and so you're left with 2x plus delta x. If delta x gets very, very small, okay, so this expression right here, which was our average rate of change function, remember this is the average rate of change function for our particular accumulation function, x squared, is essentially equal to, so this right here, this symbol right here, equals with a dot, means they're essentially the same. 2x. What was the graph that we got when we let delta x get small? It looked like this, right? As delta x got small, that the step function virtually became this line, and that's the line 2x. So this is showing that same result that we showed graphically, now showing it algebraically. Okay. Did I lose you? Anybody? Are we good? Make sense?
So how did you just get down to 2x though?
Because delta x, if delta x is small enough, it's essentially adding 0. Right? Other questions? Okay, we'll skip over that. Okay, so we've established that, what was this, the left side? What was the left side? What is that right there? That was our, so that's our rate function, which is based on, so what is this in general? What kind of rate? And we call that average rate of change, right? This is the average rate of change over an interval of delta x. Let's write that. Now, this is, in particular, it's for f of x equals x squared, right? It's only for that particular function. if we had a different accumulation function, this all would be different in the top, okay? This is based on, remember this is our left of x plus delta x, the left side of it, and then the right side, that's the right side, and then this is the left side. But it would be, the function values themselves would be different for a different accumulation function. So what does this mean? It means that these values, the values of these two expressions are essentially equal for small values of delta x. Okay? Both expressions produce essentially the same number for sufficiently small values of delta x. Or, like we talked about, there's no number between them if we let delta x get very small. There's no number between these two expressions if we let delta x get small. That's the idea of a limit. That's the idea of a limit. Two ways of representing the same number. Okay? In other words, there's no number you can find in between them. And that's true for this when delta x gets small enough. Okay? So then here's how we express that. So this idea of delta x being sufficiently small, we use this notation. Limit as delta x goes to 0. So where this was the average rate of change function, now what is this? This whole thing. Exact rate of change function. For if the accumulation function is x squared. So two different forms of the same thing. This is called open form. It expresses the process that it takes to get the exact rate of change function. This is the closed form. The closed form is the type of form that just you can spit out answers really fast, right? It's just like a standard function. You can plug in lots of inputs and crank out lots of outputs. That's what closed form is. Open form is showing that it kind of displays the process of getting that rate of change function. Whereas closed form is the one that can rapid fire for inputs, rapid fire out outputs. Okay, anybody have a question?
So what happens in the closed form? It doesn't produce numbers as quickly as the open form?
No, it's representing the process, right? It's representing the process we went through to get that exact rate of change function. Yeah. So here's the idea. If you choose a value for x and you pick a number between these two, then you can find a small enough value of delta x such that it's not true anymore. Okay? So you can always, it's kind of like a game. It's like pick a number that's between these two. Okay? Well, then I can give you a delta x such that the number you picked is no longer between them. So you can always pick a smaller and smaller delta x so that any number that's between them gets squeezed out. And so therefore, as delta x is very, very small, they're essentially the same number. Okay? And so this is the notation. So a conventional notation is, instead of delta x, you'll often see h. So h is kind of a convention that they'll use in textbooks, but delta x conveys the meaning, right? The meaning is our interval size, right? It's our interval size. So two different ways to show it. On the left, the limit as x plus h squared minus x squared over h as h approaches 0 is 2x. So that's how we say that one. The limit of this expression as h approaches 0 is 2x. This way is, we're saying these are essentially equal, so the equal with a dot over it, there's essentially equal for small values of h. Or in other words, there's no number between them. There's no number between them for small values of h. Okay, so new example. Quickly. So what here, this is, Vx is the volume of a sphere. How can we write it as an accumulation function? So how can we express, how is it that Vx is an accumulation function? It's the accumulation of what?
The volumes, the sphere as the diameter.
It's the accumulation of the volume at x as x stands for what? It's the radius, which we're calling x, increases from 0 to x. Okay, so I've got delta x set at 0.1 here. Make this bigger. Sorry. Okay, and then I've written R. Is this average rate of change or exact rate of change? That's the average rate of change over intervals of delta x. So what is R of x? Rate of change of accumulation of as the radius, no, because the rate of change is kind of at a particular value of x.
Accumulation of area over the interval. X plus delta.
At a particular radius. Okay, so accumulation is, accumulation, we accumulate volume all the way from 0 up to x. Rate of change is always it's changing, right? It's changing quantity, depends on the radius that we're at. Okay. So let's take a look at this right here. All right, we don't have time. We'll have to do this next time. Okay, so your quiz today is on stuff from Monday and Wednesday. Okay. What's that? Good try, Marcus.
The class video will be playing while we take
What's
it,
that?
right?
What's that?
You'll just play the class video while we take the quiz?
No. All right. Have you been doing that, Owen? Okay. All right. So your quiz is on Monday and Wednesday. Have a good weekend.
First Friday.
Hi.